Okay, so in this video, I'm going to be going over section 4.5. And section 4.5 is all about rational functions. So rational functions are any functions that have a fraction in them where the numerator and denominator are polynomials. And more specifically, it's any functions that have a variable in the denominator. So for a couple examples, f of x equals 2 over x minus 1. This is a polynomial or a rational function because there is a variable x in the denominator. Or it can look like x squared plus 3 over x cubed minus 4, something like this, where there's a variable in the numerator and the denominator. But more specifically, the denominator has to have a variable in it in order for it to be a rational function. So both the numerator and the denominator are considered polynomials because even constants like this 2 is a polynomial. And of course, the denominator, which in this notation is p over x divided by q over x. Those are just two different polynomials. The denominator q of x is not the zero polynomial because we cannot divide by 0. And then the domain of rational functions, which is all the x values that we're allowed to plug into the function, would consist of all inputs for x for which the denominator is not 0. So x can be all values except for the value that makes the denominator equal to 0 because we can't divide by 0. So hopefully I've drilled that into your head thus far. And that way you will remember that this is how you find the domain of a rational function. You figure out what makes the denominator equal to 0, and then the domain is all values except for that value. So let's look at this first example, this function 1 over x minus 3. F of x equals 1 over x minus 3. So I do have the picture of this graph over here, but we're going to talk about what the domain is. So if we look at this function, the denominator is x minus 3, and the value of x that will make x minus 3 equal to 0 would be 3. So therefore, x cannot equal 3 because that would make that denominator equal to 0. 3 minus 3 is 0. So therefore, it can equal any other number except for 3. So on a number line, if I plotted the number 3 and I shaded what x can be for this function, of course, there would be an open circle at 3 because it cannot equal 3. And then I would shade everything else because x can be literally anything else. It doesn't matter. The only thing that is bad is when that denominator is equal to 0. And that would be when x is 3. So any other number would be fair game for that domain. So therefore, the interval notation of the domain of this function would be from negative infinity here up until that 3 with a parentheses. And then I need to use my union symbol. And then I would start back at 3 with the parentheses and go to positive infinity. So that is what my domain would be in interval notation. Okay, so like I said, I do have the picture of this graph here. And one thing to note, remember in chapter 2, I gave you the library of basic functions, and we learned transformations with them. So this graph, the graph of and this is kind of just a side note for right now, but I just want to bring this to your attention. The graph of f of x, which is 1 over x minus 3, is the graph of, let's just call it g of x, one of our base functions, 1 over x shifted to the right 3 units. So if you remember in that list of that library of functions I gave you, 1 over x was one of those base functions. That was called the rational function, maybe? I can't remember what it was called on that page, but we'll call it the rational function. And I gave you the graph of that function, which I'm going to sketch right here underneath this. The graph of that function looked like this. You can go back and look at the files. I think it was in 2.1. This would be the graph of g of x equals 1 over x. That's what that looks like. So the graph of 1 over x minus 3 is given by the function that's almost exactly the same as 1 over x, except for I'm subtracting 3 from it. So since I'm subtracting 3 directly to the x, this is one of my horizontal transformations. And because I'm subtracting it, it's going to move it to the right 3 units. And so that is what we see in this picture of this graph here. Looks just like the graph that I just drew down at the left, but everything is shifted to the right 3 units. So that's just kind of a reminder about your transformations. Okay, now the other thing I want to say about this, we just found the domain to be all values except for x is equal to 3, because 3 makes the denominator equal to 0. So x cannot equal 3. And if I look on the picture of this graph, there's really an invisible line here, vertical line. I'm going to draw it right there. And it's kind of hard to see in this image of this graph, but that is the value at x is equal to 3, that vertical line there. And you can see that the graph, the blue parts of this graph, they will never touch that vertical line because x cannot be positive 3. So it will never cross that vertical line. It's going to keep getting really, really, really close to it on both sides. Like, for example, if I go from the left to right and follow it, it's getting really, really, really close to x is 3, but it will never touch it. And if I come from the right and I follow it and get really, really close to x is 3, it will never touch it. And again, that's because x cannot equal 3, because it makes the denominator equal to 0. So it's not in the domain. It's undefined at that point. So that's why it'll never touch it. Well, this is a vertical line, which is called a vertical asymptote. So that imaginary line I just drew, x equals 3 on that graph, is a vertical asymptote. And that is what we are going to learn about now. Okay. So just like I just said, a vertical asymptote of a rational function is an imaginary vertical line that the function will never touch. And for a rational function, p of x over q of x, where p of x and q of x are polynomials with no common factors other than constants. That's important, and we're going to talk about that a little bit later. Then if a is a zero of the denominator, which means a value that makes the denominator equal to 0, then x equals a is a vertical asymptote for the graph of that function. So just like we just seen in that example, 3 was a 0 of the denominator x minus 3. Because if I plugged 3 in for that x, it would make it 0. And therefore, x equals 3 here was a vertical asymptote of that function. It is an imaginary vertical line that that function will never touch. So therefore, if we're asked to find the equation of a vertical asymptote, all we do is set the denominator of a rational function equal to 0, and we solve for x. We figure out the values of x that make that denominator equal to 0. So let's do an example here. It says determine the vertical asymptotes and the domain of the function. So first, let's find the vertical asymptotes. And for a rational function, for rational functions, they can have more than one vertical asymptotes. It's possible. And if they do have more than one, then the function will not cross any of them. So to find the vertical asymptote, we are going to set the denominator equal to 0. And solve for x. So in this case, the denominator is x squared plus 2x minus 8. Now, I should have said, before we do this, we need to make sure that there's no common factors. So really, I'm going to put a note here. You must factor the numerator and the denominator and simplify before finding vertical asymptotes. So I am going to put that note here, but this example there won't be a common factor. But still, let's factor the top and the bottom, the numerator and the denominator. So the numerator is just 2x minus 11, so that can't be factored anymore, so that's fine. The denominator is a quadratic function, so it's in that form, ax squared plus bx plus c, and that can be factored. There are two numbers that multiply to give me -8, my c, and add to give me my b, which is 2. And that would be -4 and, -2 and positive 4. So that would be x minus 2 times x plus 4. And that is how that denominator will factor. So I've factored the top and the bottom. They don't have any common factors. So now I will set the denominator equal to 0 and solve for x. So I take the x minus 2 times x plus 4 and I set it equal to 0. And then of course I would take both of these factors and set them equal to 0 to finish solving. And so I would add 2, so x would be equal to 2. This would be one vertical asymptote, or x would be equal to -4. This would be my other vertical asymptotes. So that's it. I just found them. Those are the values that make the denominator equal to 0. Now let me make this a little bit smaller. And let's talk about the domain. So really, I just found my two vertical asymptotes, which are the values that make the denominator equal to 0. So this is actually going to also help me find my domain. Because 2 and -4, these are the values that x cannot equal. X cannot equal 2 or -4. Because it makes the denominator equal to 0, and that means that would make the function undefined. So the domain would be all numbers except for 2 and -4. So if I drew on a number line, those two numbers, -4 and 2, both of those would have an open circle because they can't equal those numbers for the domain. But it can equal everything else. So the domain in interval notation would be all three of those intervals on that number line that I have shaded in blue. So it starts all the way at -infinity and goes to -4 with a parentheses because it can't equal -4. And then it includes all the numbers from -4 to 2, excluding -4 and 2. And then finally, it has the interval of all values from +2 to infinity, but not including 2, so it gets a parentheses. So this is my domain in interval notation. All numbers except for -4 and 2. Now, sometimes in Pearson, it might just say that, give you the option to put the domain as all numbers except for the values, and then you would put 2 and -4. But these are the values that x cannot equal in your domain, because that's what makes your function undefined. I know I'm going to keep repeating myself. Okay, so I'm going to graph this function on the graphing calculator so we can see what it looks like, and you can see where these vertical asymptotes are on the graph. So let me go to my calculator here. Delete. 1 second. Okay, I'm going to go to y equals to enter it in. And then you can enter a fraction notation by hitting this green alpha button and then the button directly to the right, the xt theta, because you see that green fraction symbol up there in the top right corner. And you can see it puts a fraction up there and it's highlighting the numerator. So we enter in what's in the numerator, which is 2x minus 11. Then hit my down arrow to go to the denominator of the fraction. And you could put the factored version or the original here, it doesn't matter. I'll just put the factored version we found. So that was x minus 2 in parentheses times x plus 4 in parentheses. And then I'm going to hit graph. And so here is the graph of that function. And if I go right here, 1, 2, 3, 4, to -4, as close as I can, just put my cursor there so you can see what I'm talking about. You can see that there is this is where that first vertical asymptote is that we found, x equals -4. Of course, you can't see the actual vertical line because it's imaginary, like I said, but it's an imaginary vertical line at -4 where our graph will never cross. It'll never touch it. And if I go to second table and I look up the value of -4 up here on the x value, you can see the y value says error because it doesn't exist. There's no point at x is -4 because it'll never touch it. The graph will never touch it, so it's an error. It's undefined there. And then if I go over to +2 here, again, we have another vertical asymptote where our graph will never touch +2. It's hard to tell that in the graph, but if I zoomed out a bunch of times, well, it's still kind of hard to tell, but it'll never touch y equals to 2. See, here's my thing. That's at x 1.89, so pretty close to 2. It's never going to touch it. Let me zoom back out. Zoom back in, sorry. Okay, so that is the picture of that graph. Now, last thing, the domain is all values except for those two values, -4 and 2. All other x values, if you go to your table, you'll have a y value associated with every other x value except for -4 and 2. See, at 2 here, there's also an error. But all other numbers, there's a y value. So the domain is all numbers, because it's all values of x that are on this graph except for -4 and 2. And then the last thing I want to say about this so that I can introduce my next topic, which is horizontal asymptotes. You might be able to tell that there's this space, a horizontal space or a horizontal invisible line here that looks like our graph is not touching on the left. Looks like over here the blue piece of the graph below it is going up and getting really close to the x-axis, but it's never going to touch it, and that's true. And that is because this function also has a horizontal asymptote at y equals 0. Now there is, on this point, this side, the right side over here, the graph will cross y equals 0. But on the left side, the graph will not cross y equals 0. So this is an example of a horizontal asymptote. And horizontal asymptotes, as in this example, they can cross the graph. But vertical asymptotes, it'll never cross. Horizontal asymptotes, it might cross it on one side, but it will not cross on the other. Or it may not cross on either side. Okay? So that's what we're going to talk about now. Horizontal asymptotes. Now, just like with vertical asymptotes, the answer that we got over here for these vertical asymptotes were equations of vertical lines. X equals 2, that's an equation of a vertical line. X equals -4, that's an equation of a vertical line. And your answer in Pearson would be in the form of an equation, because it is an imaginary vertical line would be, that's what a vertical asymptote is. So for horizontal asymptotes, these are equations of horizontal lines. Y equals some number. And the line y equals b, some number b, is a horizontal asymptote for the graph f if either both of the following, if either or both, of the following are true. So if one of these are true, or if both are true. And I'm going to talk about what this notation means. Now, to talk about that notation, I am going to draw two examples of graphs up here. The first one is the graph that we just looked at. Something like this. And then the other one, I'm just going to draw the graph of 1 over x that we had. That's in our base, our library of functions. Now again, remember this is the graph of 1 over x, and in this graph, x cannot be equal to 0. So we have a vertical asymptote at x equals 0. It'll never cross the vertical line at x is equal to 0, because that's what makes that denominator equal to 0. Okay, so that's just kind of reminding you of that. And then this is the graph of the function we just looked at, 2x minus 11 over x minus 2 and x plus times x plus 4. So this is that graph. Okay. So now back to this definition. I'm going to highlight this notation on the first part here, and then I'm going to write out what that says. So again, our function will have a horizontal asymptote at the y value of b if one of these or both of these are true. So the first one says if the function f of x approaches, that's what the right arrow means, approaches b, which is the y value, as x approaches positive infinity, which means it's going towards the right. X would be going to the right, or our function would be going to the right. So it would be, x would be increasing. Not the function would be increasing, but x would be increasing towards the right. So the function f of x approaches the y value b as x approaches infinity, which means the function's going towards the right. So if I look at the function up here in this picture that I have to the left, if I was following the graph towards infinity for x, as x is moving to the right, I'd be over here. And as x is going to the right towards infinity, my graph is approaching the y value of 0. It's getting very close to y equals 0. So therefore, this function has a horizontal asymptote at y equals 0. Because that's the y value that it's approaching as x is getting closer to positive infinity. And then the other one says, this other case here, says that the function, let me put some dividers here, the function f of x approaches the y value b, or some y value b, as x approaches negative infinity. Okay, so as x is decreasing or going to the left, so on the graph on the right, up here on my right graph, the example of the graph on the right, as x is approaching negative infinity here on the left, again, my graph, the y value of that graph is approaching y equals 0. So this vertical line, y equals 0, is a horizontal asymptote. Now it's also doing the same thing on my other graph that I have here. As I'm approaching negative infinity on x, for x, not y, but as x is going to the left, my graph is approaching the y value of 0 on the left. So the picture of the graph on the left that I have there is an example of a graph that has a horizontal asymptote where both of these statements are true on the left and the right side. And the picture of the graph on the right is an example of a function where only the second statement is true, that the graph is approaching the y value, some y value, as x approaches negative infinity. And it just so happens that both of these examples, the horizontal asymptote is y equals 0, but it doesn't have to be y equals 0. It can be any y value if the graph is approaching. I just used both of these examples to show you. So both of them had a horizontal asymptote at y equals 0. Okay. So, the definition is important, but what's really important here is that we know how to find the equation of the horizontal asymptote. And so that is what this part is saying here. So to find the equation of the horizontal asymptote of a rational function, and then I have a certain kind of notation of a rational function here. So what I'm going to talk about what this notation means. So it says f of x equals ax to the n power plus ... So here ax to the n power is the leading term. So a would be the leading coefficient of the numerator. And n would be the degree of the numerator, the highest exponent of the numerator. And then the denominator, and everything else after the leading term doesn't matter when I'm talking about the horizontal asymptote. I'm only going to be using the leading term of the numerator in the denominator. So that's why I have plus ... after, because I don't care what else is up there. I only care about the leading term. Now on the denominator, this says b times x to the n power. So same thing, this is the leading term of the denominator. So b is the leading coefficient of the denominator, and m is the degree of the denominator, the highest exponent of the denominator. So that's what that notation means, okay? And I have it written like this because I'm going to use it for these three possible cases down here. Okay. And these three cases here will tell us what the horizontal asymptote of the function is. So case 1 is if n is equal to m. So I'm talking about the degrees, the highest exponent on top of the fraction and on the bottom. If they're the same degree, then the horizontal asymptote is given by the equation y equals a over b, which is the coefficients, the leading coefficients. So one way I remember that is if the degree is the same on the top and the bottom, then it'll be the same thing that you see right in front of the variables, a over b. I'm going to show you an example of that. So if I had the function 2x minus 1 over 3x plus 4, then the degree of the top here of the numerator is just 1 because of the exponent on that variable x. That's the highest exponent. And the degree on the numerator is also 1 because of that invisible exponent on x. We just don't usually write it if it's 1. But they're both just linear polynomials, so they have the same degree. So same degree means that the horizontal asymptote is equal to y equals the same thing you see in front of those variables. So 2 over 3. So y equals 2/3 is the horizontal asymptote of that function. And then the second case is if the degree on the numerator is less than the degree of the denominator. So for example, if I had 5x plus 1 over x squared plus 3x minus 2, if this was my function, 5x plus 1 over x squared plus 3x minus 2, then the degree on the numerator is equal to 1, because that's the highest exponent in the numerator, because of the 5x. And the degree of the denominator would be 2, because that's the highest exponent of that polynomial in the denominator, x squared. So here, the top degree, 1, is smaller than the bottom degree. So when that happens, the horizontal asymptote is just the equation y equals 0. So I remember that as if you have a if the top degree is smaller than the bottom, then you have a small horizontal asymptote, y equals 0. 0 is a small number. So that's just always the case, if the top is smaller than the bottom. And then finally, the last case is if the degree on the numerator is larger than the denominator. So if the top exponent is bigger than the bottom exponent, then there is no horizontal asymptote. So for example, if my function was x cubed over x plus 1, the degree on top would be 3, because it's x cubed, so 3 is the highest exponent of the numerator. And the degree on the bottom would be 1 because of the x. That has an exponent of 1. So the top is bigger. 3 is larger than 1, so there is no horizontal asymptote. Okay, so with horizontal asymptotes, there's only going to be one or none. Whereas with vertical asymptotes, we've seen that you could have one or multiple. And again, that another difference is with vertical asymptotes, it'll never cross. And with horizontal asymptotes, it may cross. It might. But it will not cross on one of either the left side, the end behavior of the left side, or the end behavior of the right. So let's do a couple of these examples here. So number 1 says to find all asymptotes of the function f of x equals 3x minus 2 over 5x plus 1. And when it says find all asymptotes, it wants us to find the vertical asymptote and the horizontal asymptote. So first we're going to find the vertical asymptotes. So remember, to find the vertical asymptotes, you factor the numerator and the denominator, and simplify. Now this is you only have to do that to find the vertical asymptotes. Okay, and I'm going to talk more about this a little later. But that is what we need to do first when we're finding vertical asymptotes. Now this function is already factored. There's nothing else I can do here. The top and the bottom is already factored. So now we will set the denominator equal to 0 and solve for x. So I take 5x plus 1 and set it equal to 0. Subtract 1 to both sides. And then divide both sides by 5. So x equals -1/5 is my vertical asymptote. I'll write VA for vertical asymptote. So that is the equation of the imaginary vertical line that this function will never touch, because that value x makes my denominator 0, which means it's undefined. And so the domain of this function would be all values of x except for -1/5. But it didn't ask me that, but I'm just reminding you that. Now for the horizontal asymptote, we look at the degree of the numerator which is just 1, because there is just a invisible exponent of 1 on that x. That's the highest exponent there. And then same thing for the denominator. The degree of the denominator is also equal to 1 because of that 5x. The exponent on the x is 1. So they have the same degree. So the horizontal asymptote is the equation y equals the same thing I see in front of those leading terms, 3/5. 3/5. So y equals 3/5 is the horizontal asymptote of that function. Okay. Number 2, we are going to find the vertical asymptotes first. So first we will factor the top and the bottom. X plus 1 can't be factored anymore. And x squared plus 3x minus 4, this can be factored to x minus 1 and x plus 4. Okay, but nothing simplifies. They don't have any factors in common, so we're good. So step 2, I set the whole denominator equal to 0. And I solve for x. So I take x minus 1 and set it equal to 0, and I take x plus 4 and set it equal to 0. So x equals 1 and x equals negative 4 would be my vertical asymptotes. And again, those are the values that make my function undefined. So the domain of this function would be all values except for 1 and negative 4. And then for the horizontal asymptote, the degree of the numerator is 1. And the degree of the denominator is 2. So the top, the degree of the numerator is smaller than 2. Smaller than the bottom. So when the top is smaller, the degree of the numerator is smaller, the horizontal asymptote is y equals 0. Always. Okay, and then finally, number 3, the vertical asymptote this is already factored, so I don't need to worry about that. The top and the bottom are already factored here. And so I can just take the denominator and set it equal to 0, add 4 to both sides, so x equals 4 is my vertical asymptote. And the domain of this function would be all values except for 4. And then the horizontal asymptote the degree of the numerator is 3. It's the highest exponent on the numerator. And the degree of the denominator is 1. So the top degree is larger than the bottom. So when that happens, the horizontal asymptote there is none. There is no horizontal asymptote. The top is larger. All right. Now, I'm probably going to split this video into 2 parts. But before I talk about, I forgot to mention this actually up here. In the third case there, whenever the degree of the top is larger and there's no horizontal asymptote, in that case only, there may be an oblique asymptote. And so we're going to learn what an oblique asymptote is also, but I'm probably going to save that for the next video. So before I do that, the last thing I want to talk about is something I forgot to put on the notes. So let me talk about that now. Okay. So I've been telling you this whole time that before you find vertical asymptotes, you must factor the numerator and the denominator and simplify. Now, you only need to do this, you only need to simplify the rational function when you're finding the vertical asymptotes. You always need to go back to the original when you're finding the domain or anything else. When you're graphing it or anything else, it's only this vertical asymptote part. Okay, so I'm going to explain more what this means. So this, when you have a common factor in the numerator and the denominator, besides a constant, and it can be simplified, this creates holes in the graph. So when rational functions share a common factor in the numerator and the denominator, this creates holes in the graph of the function. Okay? So for example, if I had the function x minus 1 over x plus 2 times x minus 1. Now this is an example of a function that's already been factored for me. So, again, they probably will give you a function and then you need to factor the top and the bottom, and then you would get something like this. If you got something like this, this function has a common factor of x minus 1 and x minus 1 because it's in the numerator and the denominator. So if I simplified this, it would be equal to 1 over x plus 2 because these would just cancel. And that would leave me with 1 on top because I'm technically dividing the top by x minus 1 and the bottom by x minus 1. And they just divide into each other and leaves me with 1 on top. And that leaves me with x plus 2. Okay? So, now when I find the vertical asymptote, I only use this denominator. that factor of x minus 1 will not be a part of my vertical asymptote answer because it was a common factor. So the vertical asymptote would come from setting x plus 2 equal to 0, because that's my new denominator, which would give me x equals negative 2. This would be my vertical asymptote. And then the hole in this graph, because like I said, when they share a common factor in the numerator and the denominator, like this example did, this is going to create a hole in my graph. And this hole will occur at x equals positive 1 because this is the value of x that makes the common factor equal to 0. If I plugged in 1 for x there, 1 minus 1 is 0. Okay. Now, the domain of this function is still all values except that what makes the original denominator equal to 0. So x still cannot equal negative 2, because negative 2 would make that first factor equal to 0. And it cannot equal, and x cannot equal positive 1. So this is for the domain. What am I allowed to plug into this function? Well, I can't plug in 1 still because it makes my original function undefined. But it's not a vertical asymptote. It's a hole. So it's still undefined at x is 1, but it's just not a vertical line that the graph won't cross. It's just a hole in the graph. And so that would be my domain. And then I want to stress one more thing about this, and that is that these two graphs are not the same. The graph of f of x equals x minus 1 over x plus 2 times x minus 1, and the graph of 1 over x plus 2, where it's simplified, these are not the same. Even though it's simplified and algebraically they're equal, they do not create the same graph. So if I wanted to graph this function in my graphing calculator, or even by hand, I need to use this equation here. Okay. All right. And if you graphed, I'm not going to do this, but if you, well, yes, I will. Let me show you what this graph looks like on the graphing calculator. All right, so I'm going to go to y equals. I'm going to type that fraction button again, alpha, the green alpha, and then the button to the right. And I'm going to type in x minus 1 on the numerator, and then parentheses x plus 2 times x minus 1, parentheses. Now again, I'm typing in the original, not the simplified version, because that would be a totally different graph. but let's graph it. Okay, so here's what my graph looks like. Remember, we found the vertical asymptote to be at -2. So that lines up. Here is around about -2 where my cursor is. And so that creates a imaginary vertical line that the graph will never touch. Okay. And then we found that at x equals 1, there's a hole in my graph. Now, you can see over here where my cursor is, this is about where, oh, sorry, right here, my bad. Here, this is where x is 1 is, around about. And the graph on your calculator is not going to show you the hole, but you can definitely see there's no vertical asymptote because it looks like that function is crossing at 1. You know, it's going through 1. Now, if I go to but it won't show you the hole, but if I go to second table and I look at the x value of 1, there is an error there still. So there's not a point there. It would just be an open circle at x is equal to 1. It doesn't exist. And so you can confirm that on your calculator, go to that value that you found to be an open hole, and there should be an error for the y value. Okay, but there's definitely not a vertical asymptote there. So if you don't factor these and simplify before you find your vertical asymptote, you're going to get the answers wrong. If there's a common factor, the common factor in the denominator will not be a vertical asymptote, but it will still be a part of the domain because that will still make the original function undefined. And it will create a hole in your graph at that x value. Okay, I'm going to stop this video here, and I'm going to make another one and post it, so that'll be like part 2 of 4.5.